Well, hello pre-calculus students and seekers of general truths. In this video, we will continue our study of sequences with the idea of a limit and how that applies to sequences. And we can understand sequence intuitively, or the limit of a sequence intuitively, as what happens as the number of terms increases. And so and also, as that number of terms increases, and what I've written here is a slightly more rigorous definition. So given a sequence where each term is a sub n, where n is some integer, the sequence converges if a sub n approaches some value L as n approaches infinity, where L is a finite number. Okay, and so what we will often write, or a common notation that we use we do this, is that if the limit as n approaches infinity of a sub n is finite, okay, is some variable L where this is finite, and I'll say this is less than infinity. Okay, let me try this again a little bit better here. Is something less than infinity, then we can say that a sequence is convergent. Okay, and divergent, well, it just means that anything that's not convergent. Okay. And divergent is actually a little bit tricky to understand. So, and all of this is a little bit tricky to understand because there are some details and notation here that we have to be careful about. So let's just look at some examples here. So first problem here, A. So this sequence is a fairly simple one, right? It's all of the integers. So we can say that A1 is equal to 1, A2 is equal to 2, and so on. And we can see that as n gets really, really large, okay, so if n is like a billion, then A sub n is also a billion. So this number, this particular sequence here, is a divergent sequence. Next, we see here this sequence, which is also explicitly defined. It's a fraction. It's the sequence of fractions where the denominator is an even number. So the first term here is 1/2. The second term here is 1/4, and so on. And we can see that all of these values are actually getting smaller and smaller and smaller, right? So as n approaches infinity, a sub n gets really, really small. So as a, I keep writing a, I want to write n. As n approaches infinity, right, a sub n is getting really small, and in fact it's getting closer and closer to 0. So another way that we can express this is to say that in example B here, the limit as n approaches infinity of a sub n is equal to 0. Okay, and one more way that we can say that this is convergent to 0. Now note here that this sequence never actually reaches 0. No matter how big the denominator gets, the fraction is still a positive number. It's a little bit above 0, but it never actually gets to 0. Okay, but we can still say that it's convergent because the term here is getting, or the actual number in the sequence is getting smaller and smaller and smaller and getting closer and closer to 0. All right, so a few more examples here. We can see here in this sequence is always decreasing, and let's see where it decreases to, right? So it starts out at 2, it gets smaller to 1.5, and then it gets smaller here to 4/3, which is 1.3, repeating. All right, so I realized there was a typo here. This should not be 5/6. It should be 5/4. Okay, so hopefully this gets a little bit more clarified here. So as we continue with this sequence, we can see a few patterns that's emerging here, right? That the numerator is a integer that's one more than the denominator. And this actually continues to go on here. And we can see that this sequence is actually getting smaller and smaller and smaller. And so in the long run, this sequence doesn't really go all the way down to 0, but it gets closer and closer and closer to 1. And so one thing we can do here is we can take the explicit definition of the sequence, so that as n approaches infinity of n plus 1 over 1, and remember we have a rational expression here, so we look at the leading term of the top, which is just n, over the leading term of the bottom, which is also n. So the limit of that explicit definition is the same thing as the limit of n over n, which is 1. Now in part D, this is a most interesting scenario. This sequence is just an alternating sign of -1 and +1. Okay, but this sequence is actually divergent. Even though it's finite, the problem with this is that it doesn't approach one finite number. It keeps bouncing back and forth between two finite numbers. So it doesn't really get closer to anything. It just keeps jumping back and forth. So remember what I said earlier, that the definition of divergent is just that it's not convergent. Okay? And based on the definition of convergent is that as n gets large, a sub n must equal L. Right? It doesn't say a sub n equals L and some other number. It says a sub n must equal L or get closer and closer to L, one particular number. In this case, in part D, that's not true, so that we can say that this sequence here is divergent. Okay. In part E, this is also worth noting here, that this sequence is alternating as well. Okay. But if you notice, what's happening with this sequence is that it's alternating signs. It's jumping back and forth between negative and positive values. And sometimes it's helped to think about the the graph of this sequence. Okay, so if we think about this, the first number is, let's say, -1/3 is like down here. Okay, so -1/3 is here. Then 1/6 is up here. It's a little bit closer to the x-axis. Then -1/9 is here. And then the next term here would be +1/12, and it's closer here. And so if you think about how these numbers are working, they're bouncing back and forth, which is fine, but in the long run, these numbers are all getting closer and closer to 0, right? So as we go on, these dots are going to get closer and closer to 0. So one thing about the definition of convergence is that it doesn't specify which direction it has to come from. It could come from the positive side or the negative side. Both are okay. So this particular sequence is convergent towards 0. It will get closer and closer to 0. We can take the limit here and we can show that that's true, that as n gets huge, the fraction is going to get closer and closer to 0. So one more example here, part F, and this is a good one to think about. We can convert these into decimals if it helps. So the first term is 0.5, right? The second term is 0.6 repeating. The third term is 0.75. The next term is 4/5 or 0.8, and so on. And this sequence is actually increasing, but it's convergent, because the limit as n approaches infinity of n over n plus 1, so remember we're looking at the leading terms on the top and the bottom, this is going to approach 1. So part F here shows us a rare scenario where you could have a sequence that increases, where every single number gets larger than the previous one, but it's still convergent because it's getting closer and closer to one specific number. Okay, so it's important for you to make all these distinctions. What's a finite sequence, an infinite sequence? What does it mean to be convergent, increasing, decreasing, and look at all of these scenarios. There's not any specific rules that you can use that works 100% of the time. You have to think carefully about each one of the series that you're given. As always, thank you for watching. Keep working hard and have a wonderful day.